one, delta CS is equal to about 0.88, and delta CA is again 2. I'm sorry, CA out is again 0. So we do indeed have something better. 0.88 is better than 0.864. It's a little better. Can I do even better? Can I do even better? Notice there isn't that much of a difference because there's only this little piece of area that I've added to the plug failure. But it is better. That was a good suggestion. If I have, for example, cheap separation, is there anything that I can do? That's better. All clear? Tell me what's, I add a recycle to
sorry.
Someone see anything? Remember, I gave you a hint earlier as to when you might use a different concept of best. Sorry? So give me a scheme. Give me a scheme. Yes, that's what I wrote in Blackboard. Give me a scheme. Volunteer? Now's your chance to shine, to make up for not knowing how to integrate. Your boss is trying to come up with a new there's a new process. You want to get out on the market as quickly as possible before the competition. You want to make as much as possible. You help the boss, or you get a promotion. I'm stuck. I'm stuck. No, that you're thinking of reversible reactions. It's not reversible.
How about CE or including a separator, separating the
Slow. So, what kind of reactor are we talking about first?
CSTR.
So you want to use the CSTR. Equal to 1/2. So you want the CSTR to be operating here at 1. So you want the concentration to be 1. Then you put a separator.
And I separate S. Separate all the products away from A. So at the top of S are 2, from the bottom I have A. So put A back to CSTR.
Okay, so let's analyze this scheme. So what I did is we have the CSTR followed by a separator. We recycle the A, and we take the RS and T out. And let's see what happens there. In that situation, my fractional yield is determined by the CSTR. The CSTR has a capital phi that's maximum. But now that's multiplied not by CA in minus CA out of the CSTR, it's multiplied by CA in minus CA out of the whole system. But there is no CA out. CA out of the whole system is 0. So therefore, I get, what do I get for this situation? I get CS out minus CS in is equal to capital phi. Well, capital phi at the maximum we already determined. Capital phi at the maximum was, where was it? Here. This was, capital phi at the maximum was this thing. capital Phi at the maximum was 2 times a half over 1 plus a half squared. So that's 1 over 3 halves squared, so it's 4/9. Times, did I do that right? Probably did it wrong. 3 halves is 9/4. Yeah, all right, that's okay. Times 2 minus 0. So what's 4/9 minus 2? 0 is 8/9. 8/9 is 1 minus 1/9. 1/9 is 0.11111. So it's 1 minus 0.111. So that's 0.88 something. 1 minus 1/9 is 1 minus 0.11111. So that's 0.8999. Is that right? No. 0.888888. Yeah. It says 0.89. In this case, I get 0.89. I made a mistake, so it's 0.89, and CA out is equal to 0. Let's just see if I can get arithmetic right, if I bothered writing down the answer. I didn't bother writing down the answer. Right, so I may have made an arithmetic mistake. See, is that correct? 1, I've got 3 halves squared, it's 9/4, 4/9 times 2. 8/9, yeah, so 0.89, so it's a little bit better than your system. So what we can see is the order of how good things are. This gives me the best. This is the second best. This is pretty close. A plug flow reactor that's infinitely long is pretty good also, but we know the practical issue that always against that is to get CA out 0 in a plug flow reactor. It has to be really, really big. And then there's the CSTR, which isn't bad either, it's just not as good as any of these other schemes. Are there any questions on that? No, because for a CSTR of this size, it goes to CA out of the half. To find out how big the CSTR is, when CA in is 2, CA out is a half, and this is the kinetics of what equation to use, which we call in this course the design equation. You have a CE in, CA out, you can then calculate how big the CSTR is. You have questions? Yes? Oh, did I plug it? Okay, maybe I made a mistake somewhere. Yeah, you're right. This, I did that wrong. This is not 0.89. It's better than that. So let's see what I get here. This is 5, and then there's delta CA. So it's 2 CA out. CA out is, I'm sorry, where am I going?
1.
Which one was, oh yeah, you're right. CS out, so instead of 4/9, I should have something else. Actually, no, should I? 1 second. No, the CSTR, oh, it should be 1, yeah. So it's 2 times 1 divided by 1 plus 1 squared. So 2 times 1 is 2 over 1 plus 1 is 2 over 4. So it's a half. Yeah, because CA out to the CSTR, my mistake. CA out of the CSTR here is 1, not a half. So 2 times 1 is 2, divided by 4. So it's a half, times 2 minus what? 2 minus 0. That's equal to 1. So it's 1, it's not 0.89. It is better. Thank you. So it's still significantly better than the other one. Thank you. Other questions? Okay, so what I'd like to do now is talk about, for the next 5 minutes, I'd like to talk about reactions in series. And I don't have a lot of time. I only have about 5 minutes, so I can't do much algebra. I know you're disappointed. I'm sure you are for the next time. But I can talk conceptually about what's going on. And what is the theme that runs throughout Leibniz-Field? As far as there's one word where the CSTR and the plug flow reactors are extreme examples of. Extreme examples of what concept? Mixing. So let's look at how mixing affects reactions in series. And I'd like to look at two situations. Two reactors. And let's say I need light. Let's say I needed light for the reaction to go. So let's say with no light, nothing happens. When I turn the light on, the reaction goes. Kind of like with roaches. When the room's dark, they're running around. When you turn the light on, they run away. This is something only people who live in New York can relate to. Okay, so I have a little light source. And I can shine light on the whole reactor. Or what I can do is I can take a little side stream with a little window in it. And I can take the same amount of light and shine it all on this little side stream. So both of them have the same amount of light. But here I shine it uniformly on the reactor. And here I shine it only on a little side stream. Now in this case, everything in the reactor is getting the same, is getting light. So there's no mixing going on here, because everything's the same. So even if I stir, I'm not mixing things that are different. So this is a situation of no mixing. And this is a situation where when I shine light on this stream has had lots of reaction, whereas what's in the reactor has stayed the same. So when I mix them back, I'm mixing streams that are very different. So this is lots of mixing. And I'd like to think about A, R, and S, how they change with time in both of these reactors. So when I shine light on the reactor, I turn the reactions on. And if the light is shining the whole time, the reactions proceed in a normal way. A goes down, I make R. Initially I have very little R, so A is going to go down. A is just going to go down one time. Initially I have very little R, so I start producing R. And this reaction is negligible because I don't have very much R. So I'm making R. But eventually, once I get enough R, this reaction starts becoming significant. And this reaction slows down because A is petering out. And eventually this reaction takes over. So R goes through a maximum and then starts decaying. And I should have done that blue. And of course, this reaction doesn't turn on until I have some R. So initially, I don't see much S at all. And then this starts building up. I produce S at the fastest rate when R has a maximum. It's the sharpest. And beyond the maximum, this trails off. And in fact, A plus R plus S all have to add up to a constant. They all add up to 1. So this is nothing special. This is what I've seen before. We've seen before when we did the batch reactor with plug flow. How about this situation? So now I'm going to bombard a little amount of fluid with a ton of light. So what happens as time goes on? As time goes on, and I'm going to need your help here, I start out with pure A. Now I take a little A out of the reactor. This is a tiny side stream. And I bombard it with light. So initially I have pure A coming in here, and what's coming out of here? Well, someone raise their hand. This is a ton of light. Down. So there's no R, because it's all been converted all the way to S.
So you're saying 1 and 2 are both like
Yes, yes. So I have, and now the rate at which A is decreasing, here it decreased, if this is the first order reaction, it decreased exponentially. First order reaction is done exponentially. Here I have a constant, well, here it's also going to decrease. So A is going to decrease. Because it's going to decrease in proportion to the amount of A that was in here. So as A goes down, it decreases. However, I'm not going to see any R, because pure A entered here, and pure S came out. So R stays down here. On the other hand, S is going to grow. Because as A decays, S is going to grow, and the two have to add up to 1. So notice, what's the take-home message here? The take-home message is when I mix, is going to be worse for the intermediate than when I don't mix. So if I'm interested in the intermediate, generally, if I'm interested in R, generally do I expect the plug flow to do better or the CSTR to do better? The plug flow, because there's less mixing. That's my expectation. We'll do the algebra next time. Okay, 2 issues. Issue 1, AICHE meeting. Some people are going away in the AICHE meeting. When are you leaving? Friday, one time.